Let me start by introducing our speaker today. It's Professor Aleksey Cherman from the University of Minnesota. He got his PhD in 2010 at the University of Maryland, College Park, with Thomas Cohen. He had several postdoc positions between 2010 and 2012. He was at the University of Cambridge. Between 2012 and 2015, he was at the University of Minnesota. And then he was a postdoc at the Institute for Nuclear Theory at the University of Washington between 2015 and 2016. And then he became acting assistant professor there at INT between 2016 and 2018. He moved to the University of Minnesota as a tenure track assistant professor in 2018, and he's there right now. And with that, I'll give the microphone to Aleksey.
All right, thank you, Igor, for organizing all of this, and thank you to everybody for coming to listen to this. So I'd like to tell you today about some work that I've been doing over the last couple of years, which I've tried to summarize in the title, so it's sort of aimed at trying to answer the question of what is quark matter, in a sense. Before I begin, there's a couple of things I want to say. So this is a colloquium, so the idea is to explain the basic ideas that are new, and also some of the ideas that are older that I'll review that go into this kind of question. So if you want to know more about technical details, feel free to have a look at our papers or just ask me. The other thing is that, again, because it's a colloquium, I'm not going to be super careful with references for everything. I'll just try to give the big picture. And the work is with some wonderful collaborators. So Larry Yaffe, who is at the University of Washington, Srimuyi Sen, who is at Iowa State, and Theo Jacobson, who is a wonderful graduate student at the University of Minnesota. Well, let me just dive right in. So the title of the talk is, what is quark matter, right? It's a question. This question may, depending on your background, I guess, may sound interesting. Perhaps you're here, so maybe you think it's interesting. You might think it's a weird question, maybe you even think it's slightly boring, but you're hoping I'll tell you something about it that might be interesting. You might think it's an easy question, or you might think it's super difficult. If you've thought about these kinds of things a lot, you might actually think that it's a question which would only be interesting to people who are really, really into formal quantum field theory questions. Or maybe it's some from each, okay, some combination. So my goal today is to try to convince you that this silly sounding question, what is quark matter, is first, a really hard question. It's not remotely easy, but it can be answered. At least there's a plausible, interesting seeming answer. And second, that the answer is interesting not just for a quantum field theory person. It's interesting even if your interests are more practical, if you want to say something about the world and not just say something about the structure of quantum field theory. Okay, so let me dive into the guts of things. So for this kind of question, what is quark matter? There's an obvious answer, right? Quark matter is just matter made out of quarks. We're done. This is sort of fine, but it's also useless because everything is made out of quarks, right? If you look at a random atomic nucleus, it's got protons and neutrons, they have quarks in there. So it's a kind of quark matter, but that's not what anybody would really mean when they say quark matter, even though this most obvious definition would say that this is quark matter. So that's clearly not a good answer. What might seem like a better answer is, of course, the following, that quark matter is some kind of matter which is best described in terms of quarks as opposed to anything else, okay? And that just means that the quarks are natural degrees of freedom. But that raises a bunch of issues, that kind of answer. Well, one immediate issue is, okay, well, where would you expect such a system that's described best in terms of quarks to occur physically? We'll talk about that in a second. Another thing, though, is that this definition sounds kind of fuzzy, right? Is it just a matter of taste, whether you should use quarks or hadrons, like baryons, to describe a given chunk of matter? How do you know? How do you tell whether you have quark matter as opposed to something else in any precise way? Is there a precise way to tell? And finally, why is this interesting? Like, why is answering this kind of question at all interesting? It sounds like a mathematical definition type of question, so who cares? So I want to try to answer these questions, or at least give you my answers. So first, let's start with where do you physically in nature find quark matter in the sense that I mean when I say quark matter. So first, let me just remind you, since this might be a somewhat diverse audience, that if you take matter and squeeze it to high densities, the highest density matter, which is kind of relevant to us normally, is something called nuclear matter. So that's the matter inside atomic nuclei. And the density is something like a nucleon per femtometer cubed, roughly, ignoring factors of pi and so on. But if you want to, for matter like that, the right degrees of freedom are protons and neutrons, studied in nuclear physics. But if you can squeeze matter to higher densities, then the protons and neutrons might overlap, and you might have a situation where the effective degrees of freedom are really quarks. And you can reach these higher densities in remnants produced by core collapse supernova explosions. So such supernovas can leave a neutron star remnant, and a neutron star is something which has a couple of solar masses worth of stuff packed into roughly a 20 kilometer diameter. So it's extremely, extremely dense. In neutron stars, the protons that used to be there, they capture electrons and they turn into neutrons. And that's why they're called neutron stars. So neutron star cores are the highest density matter in the known universe. And for comparison, normal nuclear matter has a baryon number density, which is like 0.16 inverse femtometers cubed. In the cores of neutron stars deep in the core, we don't know exactly how dense they get, but we expect it to be much higher than that. So whatever is inside the cores of neutron stars, it's far from obvious that it should be described as nuclear matter, and it is quite possible that it should be described as quark matter, at least given the colloquial definition that I just gave you, namely that it's matter where the right degrees of freedom are quarks. It's at least plausible. Now, if we want to ask about what kind of matter you have inside the core of a neutron star, what you need to understand is the phase diagram of matter governed by strong interactions. And that's really the statement that you need to understand the temperature density phase diagram of quantum chromodynamics, QCD. Now, what do we know about this phase diagram? In parts of it, we know a lot. So if you ask about what happens at high temperatures and low densities, relatively low baryon number densities, then we have wonderful experiments and powerful numerical techniques that allow us to predict and to check what happens. So we can do heavy ion collision experiments, for example. One can perform numerical lattice gauge theory calculations and learn a lot about this regime. And that's the top, thousands of people work on this. If instead you make the density high and the temperature low, things get way harder. Because then there are no direct experiments that we know how to do. You can't do lattice simulations because of something called the sign problem. And really, for much of the higher density, low temperature phase diagram, we have to rely on models to predict what's going to happen. And those models don't have controlled error bars. So we're extrapolating away from what we know, and we don't have a controlled technique to do the calculation. So nevertheless, if you make the density ridiculously high, okay, arbitrarily high compared to the typical scale of quantum chromodynamics, it's definitely true that the quarks are the right degrees of freedom to describe what's going on. That happens because the typical quark-quark interactions end up involving large momentum transfers at high densities, and once that happens, since QCD is asymptotically free, that means that the characteristic interactions between the quarks become small, and then the quarks basically act, at least to a good approximation, as free particles. And in that sense, they're deconfined at very high densities. This is speaking loosely for now. Okay, so here's a picture of deconfinement. So here is a cartoon QCD phase diagram. Okay, the real thing is more complicated. I've only drawn the sort of broad brush features that are of interest to me on this phase diagram, and I've drawn it for the simplest possible choice of parameters that is sort of worth thinking about and thinking about such phase diagrams, which is QCD with the real world value of the number of quark colors, which is 3, and 3 light quark flavors, with, for simplicity, I was assumed for this diagram that they have the same mass, which is not true in the real world, but it's not a horrible approximation for some purposes. This is just to give you an idea. So here's the temperature, and here's a chemical potential for baryon number. So that's just a proxy for density. So if you crank up chemical potential, you're cranking up density, basically. So what are the features in the diagram? So if you go to high temperatures and low densities, you have a quark gluon plasma. If you are looking at low temperatures and small chemical potentials, you have some kind of gas of hadrons, which melts into quark gluon plasma. And I haven't drawn any phase transition curve here because there isn't one. As far as we know, there's just a crossover. Now, if you crank up the chemical potential, or equivalently the density, at low temperatures, then at some point you make nuclear matter. And well, nuclear matter, it's something where the right degrees of freedom are protons and neutrons. And in that sense, it's confined. And if you keep cranking things up, you're going to make quark matter, in the sense that the right degrees of freedom will appear to be quarks. And to the extent that the right degrees of freedom are quarks, it's not confined. And I put a question mark here because we'll have to talk about what that means. Okay. And somewhere in between, okay, lies the regime we really want to understand, which is the cores of massive neutron stars. And we don't know exactly where because we don't really know the detailed equation of state of dense matter. Good. So I'll talk more about the features of this phase diagram in a bit, in particular why I've drawn some curves here. So those are phase transition curves. I'll talk about why they're there soon. Okay. But let me just move on for now. So the question I really want to ask is, when you look at this diagram here, sorry for flipping back and forth, is quark matter a distinct phase of matter from nuclear matter? That's really the question. If it is, then there's a sense in which you can say, what does it mean to have quark matter? It becomes a sharp question. If it's not a distinct phase, then that's a fuzzy question. Okay? So really, it's like asking, is the difference between nuclear matter and quark matter like the difference between liquid water and steam, or the difference between liquid water and ice? Right? So we all know the phase diagram of water. And if you look at the pressure temperature phase diagram of water, you can go from liquid water to gaseous water to steam through some smooth path in parameter space. I mean, that's not the path that we normally take when we boil a pot of water on the stove, but there is a path, if you vary pressure and temperature, to go from one to the other smoothly. So in that sense, liquid water and gaseous water are not really distinct phases of matter. However, both of them are distinct from ice. Okay, so you cannot go from, say, liquid water to ice without going through a phase transition. And we sort of all know this. This is like basic, either high school or college stuff. So the question is quark matter like the difference between this and this, or the difference between that and that? Okay, that's sort of the question of the talk. So now let's talk about why you should care about this question. Suppose we understand quantum field theory well enough.
Sorry, Aleksey, quick question.
Yes, of course.
Why you do not assume the possibility that the quark matter could also be as ice and as water? Because in principle, you could have crystalline phases of quark matter.
You could have crystalline phases of quark matter, and you're saying the nuclear phase could be some crystalline phase, and
no. I'm saying that the quark matter itself could have two different possibilities, like crystalline quark matter and water-like quark matter. Perfect.
Good. That's a great question, actually. There may well be, and I think there are, a number of different quark matter phases, depending on the parameters of QCD, depending on exactly what you choose for parameters. I'll come back to that. So quite soon, I'll try to formulate the question in the simplest possible context, where it appears that the minimal possibility that is consistent with what we know is to say that there is some quark matter phase and some nuclear matter phase, and the minimal possibilities just go directly from one to the other. But it is logically possible there are other things in between. Like it's hard to exclude that strong coupling, especially.
Okay.
Yeah. Thank you. That's a good question. Yeah. But yeah, I mean, suppose that we understand quantum field theory well enough to be certain that quark matter is a well-defined phase of matter, which is really distinct from other phases. Okay. Well, then there must be a phase transition as you vary the density. And that would be a model-independent prediction. It would not rely on whether you've made the right assumptions about interactions in some nuclear potential model. Okay? It would really be a model-independent prediction. That would be great, because it's not like it's easy to check what happens inside the core of a neutron star. So if you have some insight from quantum field theory that's a model-independent prediction, that would be very powerful. And by construction, whatever this phase transition is, it would have to be taking place right in no man's land where we don't know how to calculate. But it's also the most interesting place. So I think that makes it worth thinking about the general quantum field theoretic question of what is quark matter. So this is, so now I've written the question as a picture. So is there some kind of phase transition curve here? Or can we argue from principles of quantum field theory that there must be one? That's the question. Okay. So on this picture, that there's something that says confined here and it says not confined there. So the most obvious thing is to say that quark matter is some kind of deconfined version of QCD. Let's interrogate that a little bit. So in QCD, quarks are in the so-called fundamental representation. Probably most of you know what that means. If you don't, just go with it. It's a statement about how they couple to the gluons. And what that ends up implying is the following. If you take two quarks in, say, a meson, and you try to pull them apart, that's what's illustrated here. At first, you make a flux tube. They're connected by some kind of color flux tube. But if you pull more, the flux tube will break. That's a feature that happens when your quarks are in a fundamental representation of the color group. So QCD, on the one hand, sort of has flux tubes that connect quarks, but sort of doesn't because they break. Okay. If you start thinking about this on a more technical level, you quickly realize that this phenomenon that I just described makes it very, very hard to give a precise definition of what you even mean by confinement in theories with fundamental representation matter, like QCD. And in fact, people who think about this kind of quantum field theory question for a living, many of them would tell you that it's impossible to give such a precise definition. Like there are good technical reasons to think that you cannot give a definition like this. So we'll come to some of those reasons shortly. So that poses a problem, okay? Because on the earlier slide, I said, okay, I have confined nuclear matter, I have deconfined quark matter, but apparently saying that is kind of meaningless. Like there is no precise definition of what you even mean by confinement. So things are getting complicated. So to keep things under a little bit of control, let me now, from now on, focus on the very simplest case of the physics of QCD. So make some simplifying assumptions just to avoid losing my hair. So I'm going to assume that I have three quark colors. That's true in nature. I'm going to assume that I have three flavors of quarks with identical masses. So up, down, and strange for me will have identical masses. And this is not a great assumption for some purposes, and it's a perfectly fine assumption for others. And I want to say that at least if you go to very high densities, the effect of the non-equality of the quark masses is suppressed by the chemical potential. So it's actually not a bad approximation. It's actually a great approximation for very high densities. But I'll just assume it for all densities, just to make it simple. And we'll see that already here, in the simplest corner of the parameter space of QCD, it's really hard to answer these questions for some interesting quantum field theory reasons. So, good. So now comes another proposal that if you study the literature on QCD, you might make for an answer to the question of what is quark matter. And that would be to say that quark matter is the Higgs phase of QCD. So what do I mean by that? So if you have very dense quark matter, there's some Fermi sphere of quarks. They're fermions, of course, so they make a Fermi sphere. but the Fermi liquid is unstable to quark pairing interactions. Those quark pairs can Bose-condense, and they do at sufficiently high densities. Well, there's some kind of hairy-looking formulas here, so don't worry about them too much. But the basic idea is that the quarks have color and flavor labels. And the way they condense, the color and flavor labels get locked together in some special way. And what turns out to happen is that the pairs of quarks have the quantum numbers of a bunch of color fundamental scalar fields. So you can call them Higgs fields because they both condense. So they will Higgs SU3 color. And the precise way in which all this happens, at least at very high densities, is something called color flavor locked superconductivity. It was studied a lot by many people in the 90s and onward since then. Basically, high density QCD is a Higgs phase of QCD. So there's the Anderson-Higgs Angler-Brout mechanism at play, and SU3 color is completely broken. And there's no obvious trace of this in normal nuclear matter. We don't normally think of nuclear matter as some kind of Higgs phase. But before I move on, I just want to say one other thing. Actually, both the nuclear matter phase that I'm interested in and quark matter are superfluids, okay? So cold nuclear matter is a superfluid in the sense that the baryons in nuclear matter can pair and condense. And so you break baryon number symmetry spontaneously. For example, in actual normal nuclear matter, the neutrons want to pair up and condense. So in a sense, it's like a superfluid, but it's built out of confined looking constituents. So that's meant to be nuclear matter. And as it turns out, quark matter, cold quark matter, is also a superfluid because the non-gauge invariant statement that the quark pairs pick up an expectation value implies a gauge invariant statement that some 6 quark gauge invariant operator picks up a VEV, but you can think of this thing as a baryon and that thing as a baryon. So it's really, again, a baryon pair picking a VEV. So again, baryon number is spontaneously broken in the same way as here. And it's also a superfluid. It just looks different because naively it's built of quarks. So that's my artistic rendition of the superfluid quark matter. Okay. So actually, that's why I had some of these lines on this earlier diagram, okay? So that's why I have this line, for example, and this one, okay? They are delineating where the baryon number symmetry is restored. So at high temperatures, it's restored. At low temperatures, the baryon number symmetry is spontaneously broken. Good. So obviously, quark matter is the Higgs regime of QCD. Well, that's also not right. Thing is, we know many other examples of places where the Higgs mechanism is important. So superconductors, the weak SU2 gauge group, and so on. People have thought a lot about it. And unfortunately, things here are just as subtle as for trying to understand what you mean by confinement. See,
Aleksey?
The way we introduce the Higgs mechanism in textbooks, usually, is we draw pictures of the Higgs potential and we say, oh, the Higgs picks up an expectation value. Oh, you know, the W bosons are some physical massive states and so on. And all of this is very useful, intuitive stuff. We can use it to calculate things. But if you dig into it, it's not technically correct. So some of the consequences derived from it are correct. Yes?
There is a question. Tanmay, which everybody?
Actually, I have 2 questions. I mean, in superconductivity, I think you have to work quite hard to show that the electrons will form Cooper pairs. So the first question is, how do we know that quarks condense in this way?
Good.
And the other question has to do with the phase diagram, which is that 2 people consider the phase diagram when there's a magnetic field as well.
Good. So let me answer the second question first. Yes, people definitely think about influence of magnetic fields, but I won't talk about it for my purposes. There may well be actually experts in the audience who have done a lot of work on it. Indeed. So people also turn on magnetic fields, yes. For your first question, in normal superconductors, you need interactions of the electrons with the lattice, and it's pretty complicated in detail to show that you have some attractive interaction for the electrons. In a sense, it's easier in QCD because you have gluons. And it turns out that there's an attractive gluon interaction in the 3-3 color channel. And, you know, that's enough.
And
so
that's
any,
enough.
as you know, like if there's, for example, the interaction is also in the S wave, and Fermi liquid theory says that any attractive interaction, if it exists, will destabilize the Fermi liquid, and you'll get a superconductor. It's a very interesting superconductor, though. Like if you are very careful and you stare at this formula, you'll see there's a G here, which is G Young-Mills. It's not G squared. In a normal Fermi liquid, if your starting point was really a Fermi liquid, it would have been G squared. So it's like a non-Fermi liquid type of thing. So it's a very interesting, highly non-trivial thing that people understood in the 90s for how this works. But the basic idea is just the gluons. The gluons give an attraction.
And then in superconductors, they talk about S wave, P wave, D wave.
Yeah.
Are those questions relevant here?
They are. You have to think about that. But in the limit that I'm focusing on, where you have degenerate quarks in the sense that they all have the same mass, the channel with the sort of highest attraction is the S wave. So this is a scalar.
Oh, okay.
Yeah.
Thanks.
It's not at all meant to be obvious, by the way. So this is all like a result of many papers by people before I got involved in physics.
I see.
Yeah.
Wow.
Beautiful work. I'm happy to tell you references if you want after the talk.
Sure, that'd be great.
Yeah. Excellent. So what I was going to say is that, you know, the Higgs mechanism itself is a bit of a fuzzy notion because the whole idea of a spontaneously broken gauge symmetry is a bit of a fake, right? Gauge symmetry is not a symmetry, it's actually redundancy. If you study the literature, you discover that a gauge non-invariant operator cannot have an expectation value, which isn't zero. That's Alitzer's theorem. Physical massive gauge bosons are also a bit of a subtle thing. So like if you dig into things, it turns out that even in the Higgs regime, all the physical states are still secretly some kind of hadrons. It might not be the most useful way to describe them in a practical calculation, but technically that's what they are. So what that means, the upshot, is that it is just as hard to precisely define what you mean by the Higgs mechanism in theories of fundamental representation matter as it is to define confinement. It's like really, really hard and perhaps impossible. So now we're in the following situation. We've at least reduced the question of what is quark matter to a more field theoretic sounding question, which is, are the Higgs and confining regimes of theories with fundamental representation matter distinct? Or are they the same? Okay. So that's now the question. And before I dig into that question, I just want to say that there is one kind of situation in which it's just totally obvious that they are distinct. And I want to tell you about it and then not talk about it again. And that is if your Higgs field is charged under some global symmetry, then naively things are very easy, because if the Higgs field is charged under global symmetry, then if it picks up an expectation value, Landau and Ginzburg tell us there's a phase boundary between that and the case where it doesn't. Okay? That's all fine, but it's not like, that's just standard global symmetry breaking. Okay, it's not really tied up with confinement versus Higgsing per se, and it's not even really relevant to QCD, because nuclear matter and quark matter have identical global symmetry realizations. So I've emphasized that they're both superfluids. If you look at the chiral limit where the quark masses are 0, they both break chiral symmetry in the same way, etc. So yeah, so they're not distinguished by global symmetry. So that's actually what makes it hard. I'll have to come back to this in a second, actually. So there's a slight swindle happening on this slide, but we will come back to it in a second. Keep this in mind for now. We are very, very far from the first people who have asked these kinds of questions. They've been studied intensively by people since the late 70s. And what the famous result in that literature is the following. So you want to avoid a boring phase boundary, the one I just told you about. So you assume that the Higgs scalars are not charged under any global symmetries. And then people have established something called the Fradkin-Schenker theorem, which was the output of a whole bunch of papers, really. And what those papers have established is that in certain interesting specific models, Higgs and confining regimes of quantum field theories with fundamental matter are smoothly connected in this sense, right? Just like with water and liquid water and gaseous water, okay? You can go from one to the other, avoiding any phase transition. Now, the basic insight that goes into these papers, abstracting away from all the technical details, is that there are no gauge invariant order parameters that you could come up with, at least it seems, that could distinguish the Higgs regime from the confining regime. And that's why there's no phase boundary. If there's no way to distinguish the two regimes in any gauge invariant way, then that's it. There shouldn't be any phase boundary. And that basic insight seems very general, right? That has nothing, this insight has nothing to do with the details of the techniques people used to make the proofs. And in fact, it seems so general that by now, what is it, 40 years more later, there's a Folk theorem that says that there are no non-trivial phase boundaries separating Higgs from confining regimes in gauge theories with fundamental matter in general, not just in the specific models that people studied back then. And actually now, let me give you the standard answer to the question in the title of the talk. People have answered it already in the 90s. Okay, there's something called the quark-hadron continuity conjecture due to Frank Wilczek and Thomas Schaefer, which is that there is no phase boundary separating nuclear matter from quark matter in the SU3 flavor limit, the limit that I'm working in. And they proved in their work that there's no Landau paradigm reason for a phase transition. There's no global symmetry difference between these things. And they appealed to the Fradkin-Schenker result, or at least the Folk theorem version of that result, to argue for their conjecture. It's a very plausible conjecture, actually, based on what was known in the 90s. Our claim is that actually there is a reason to expect a phase boundary. So we think that the confining regime of QCD, namely the nuclear matter regime, that's what we're talking about, it has a spontaneously broken U1 symmetry, baryon number. It's separated by a phase boundary from the Higgs regime, which also has a spontaneously broken baryon symmetry. So these are two distinct superfluids. So our claim, slightly more precisely, is that there exist non-trivial phase boundaries between U1 broken confining and Higgs regimes in some gauge theories with fundamental matter, in particular QCD. Those regimes are identical within the Landau paradigm for classifying phases of matter. And also, if you dig in and study what the Higgs fields are like in QCD, they're charged under the global symmetry. They're charged under the baryon number. But the Higgsing and symmetry breaking connection I advertised like 3 or 4 slides ago was totally model dependent. It doesn't apply in QCD. So, so that was a swindle, okay? And the fact that there is a spontaneously broken global symmetry in both phases, the same global symmetry, allows us in a second to define an interesting gauge invariant order parameter, which takes different values in the two regimes and indicates the presence of a phase boundary. So that's how we argue for this claim, basically. Okay. And we believe that having defined this order parameter and shown that it has the behaviors that it does, provides quite strong evidence against the quark-hadron continuity conjecture, implies a new phase transition in QCD. So let me tell you about that in what remains of my time. So we're trying to understand whether so we've now abstracted things a little bit, right? So we're not just talking about QCD. I mean, we are, but it's a bigger question, okay? We have some gauge theory with fundamental representation matter, like quarks. It's got a global symmetry, a U1 global symmetry, and it's got a Higgs regime where that global symmetry is broken, and a confining regime where that global symmetry is broken in exactly the same way. So you have two different superfluid regimes. So are they the same? Well, they are the same within the Landau-Ginzburg paradigm. They're not distinguished by any local order parameter. Now, if you follow condensed matter physics over the last, I don't know, 20, 30 years, of course, we're way beyond Ginzburg-Landau. But people use ideas like topological order all the time, including in this colloquium series. But in this case, there's no reason to expect any standard topological order to play a role either, actually. These systems are gapless. Topological order typically at step 0 assumes a mass gap. There are no useful higher form symmetries. There are no extra ground states if you compactify the theory to some manifold with genus G or nothing like that, okay? No trace of any obvious topological order. And yet we claim that they're distinct. So to do it, we're just going to have to define an order parameter. And it has to be somewhat natural, but it will not be local, because if there was a local order parameter, that would have been Ginzburg-Landau. So let me tell you about the order parameter. So first, we're talking about superfluids. Superfluids have two features that are intimately linked to each other. So because there's a spontaneously broken U1 global symmetry, first, there's a vanishing mass gap due to the existence of a Nambu-Goldstone boson. And second, there are vortex excitations. So here's a vortex, although not in a superfluid. This is a picture of a superfluid where you have a bucket of superfluid, roughly speaking, and you're increasing the rotation. And you make a vortex at some point, and then you make a bunch of vortices, and then you make more and more and more. You can even make vortex loops. They don't have to be straight. There are many, many things you can do. But the basic idea is that the vortices, at least straight vortices, appear due to rotation in superfluids. And neutron stars definitely rotate, so they have a huge number of vortices in them. Now, why am I talking about that? Well, if I have a vortex, then what it means to have a vortex is the supercurrent has some winding number around some line, right? That's what a vortex is. And since I have lots of vortices, it's meaningful to ask, how do other particles, for example, the gauge charged particles in the theory, interact with vortices? So let me make this precise. So suppose you have a vortex. Here, the black curve is a vortex, and actually I've drawn it as if it's a vortex loop. Could be straight as well, pick your poison. And then I imagine I have some gauge charged particle, let's say a quark, which I take in a circle in a way that has some linking with the vortex loop. Okay, so it goes around the vortex. And now the thing I can ask is, does that particle pick up a phase as it goes around? That phase, if it's there, would be Aharonov-Bohm phase. We're very used to such things from basic undergrad quantum mechanics for electromagnetism, but nothing stops us from asking this question on abelian gauge theory as well. So in quantum field theory, the way you get at this information is by calculating a Wilson loop with this contour. And the phase of that Wilson loop, if it's not trivial, is the Aharonov-Bohm phase. You can think of that as being determined, of the Aharonov-Bohm phase as being given by the magnetic flux through the surface bounded by the loop. And here magnetic flux is in quotes because to the extent that's at all meaningful, it's some kind of color magnetic flux, but that's also in quotes because color magnetic flux is not gauge invariant, but the Wilson loop is. So the Aharonov-Bohm phase is actually gauge invariant and hence physical. So we can ask about it, we're allowed. And our order parameter is nothing but this Aharonov-Bohm phase. Now, on a slightly more technical level, you can ask, well, how are you going to get it? Like if you do a calculation, how do you extract it? And the answer is technically, you should compute the Wilson line on a contour that goes around the vortex. That's in the numerator, divided by a Wilson line of the same geometry where it doesn't go around the vortex. That will make various non-Aharonov-Bohm phase factors cancel. So like technically people who know about perimeter laws, that'll make the perimeter law pieces cancel. And what will be left will be the Aharonov-Bohm phase. And you want to make sure these contours are pretty big. Because if they're very small, then you're probing some short distance stuff to do with the vortex. You're not probing long distance physics. So you may ask about a big contour. So the particle goes far from the vortex. But you know, in the colloquium, I won't really talk about this funny ratio that much. I'll just talk about the Aharonov-Bohm phase. But on a technical level in our papers, this is what we talk about. Okay. So now I can actually skip ahead and tell you the answer, our answer at least, to the question in the title of the talk. What is quark matter? Well, what we find is that this Aharonov-Bohm phase for vortices, color Aharonov-Bohm phase, is trivial, that is 1 in cold nuclear matter. And quark matter can then be defined as the phase where superfluid vortices carry non-trivial, that is not 1, color Aharonov-Bohm phases. So in the simple limit that I'm going to be talking about, namely the one with the quarks all having the same mass, that Aharonov-Bohm phase in the quark matter regime is e to the 2 pi I over 3. Okay, but so it's definitely not 1. So that's this thing right here is the sense, if you want, in which quark matter is deconfined. Although I don't know if that's the right language because I don't know how else to define deconfinement. So anyway, so that's our answer. So let me try to tell you how we came to this. So the first thing I want to do is I want to tell you why you should expect, without any calculation and just at the level of hand waving, why it must be true that this Aharonov-Bohm phase is just one in cold nuclear matter. So let's talk about that. Let's say I have a vortex. It's going straight at you through your screens. Okay, and you take, oops, sorry about this. How do I, just a minute. So if you want to physically ask, what is a Wilson loop? What does it do? It's describing the following physical process. You take a quark-antiquark pair, nail down the antiquark, take the quark and move it around and let it annihilate with the antiquark eventually. That's what it's doing. So let's talk about that process. I have a quark-antiquark pair. I start separating them, and at first I make a flux tube, right? I have confinement. And then, well, if I stretch them too far, the flux tube will break. And I'll pop a quark-antiquark pair out of the vacuum. And then now this is some dressed state, which looks like a meson. It's got a quark and some antiquark that came out of the vacuum. And this thing is also a meson-like thing. And now I drag around this meson, and it comes back and annihilates with the other thing that was there. That's what the Wilson loop does in the confined phase. The point of all of this is that this Wilson loop is exponentially dominated by physics that is close to the curve C. And close here means basically within the size of a heavy light meson. Heavy because this test charge that I'm introducing is heavy, and these are the dynamical quarks. So it only cares about the physics right there. And so when I look at this ratio and I compare the case with the vortex and without, it doesn't care that there's a vortex because the entire contribution to physics is coming from right there. And so as you take the limit where you're far from the vortex, you get 1 for the ratio. So the Aharonov-Bohm phase is just 1. Okay, that's what we should expect. At least one way to argue for why there are no interesting color Aharonov-Bohm phases around vortices in superfluid nuclear matter. The more difficult and, well, the more computationally involved discussion is what is this Aharonov-Bohm phase in quark matter. The quark matter, as I've said before, is you can think of it as some kind of Higgs regime, and in fact, it becomes a weakly coupled Higgs regime provided the density is ridiculously high. So we can take advantage of that and ask what happens to these kinds of questions when the density is very, very high, where we can do honest calculations on a piece of paper. And here the argument necessarily becomes more technical, so please bear with me. There are kind of 2 steps. The first step that I'll take is we will evaluate this Wilson loop in the high density limit, and that's a classical calculation if you use an appropriate effective field theory, which is what we will do. So we'll get some result. That result will be that the Aharonov-Bohm phase is e to the 2 pi I over 3. And then there's a harder step, which is to show that there are no quantum corrections to that. So that result is exact within the quark matter phase. That is, again, some use of effective field theory, which is somewhat more involved. So it's more complicated. This diagram of some control panel from a Concorde is meant to illustrate complicated things, apparently. But let me just dive in. So the order parameter, the Higgs field in high density quark matter, you can think of it as some kind of 3 by 3 matrix where it's color and flavor indices for the matrix. That's the 3 and 3, 3 colors, 3 flavors. And then, I don't expect you to follow every line here, just showing this to you to show you that we did some work, but the way you describe a vortex in this quark matter regime is to say what this order parameter field does. So it winds in some way. So this is how a vortex looks like. And here W is the winding number. So for us, it's actually 1 or -1. So we're going to consider unit winding vortices. And we're going to allow the gauge field to do whatever it wants to do. It might choose to be completely trivial and 0 in the neighborhood of vortex or not. We just solve the equations and see what happens. And if you actually do this, you discover that the gauge field, the color gauge field, does not want to be trivial, at least not completely trivial. So the way it works out, if you solve the equations, is that the trace of the Wilson loop around the vortex is e to the 2 pi I over 3, at least at tree level. Okay, so again, not expecting you to follow how that arises, but it's really just like a straight ahead vortex physics calculation, standard, that's the result. The more subtle step, which I also won't do justice to, is to understand what happens when you take into account quantum corrections to that. And it turns out to be possible to argue that the quantum corrections do not change the answer. And the reason for that ultimately is that vortex energies for global vortices, which is what we're dealing with here, are log divergent with the volume of the system. That actually constrains which terms in an effective field theory can contribute to the long distance behavior of the Wilson lines. You can classify all such terms and study their properties, and it's possible to show that they cannot, so long as this effective field theory is valid, you cannot deviate from e to the 2 pi I over 3 for the Aharonov-Bohm phase, even after quantum corrections are taken into account. So that result is really a robust feature of the quark matter regime. So this Aharonov-Bohm phase is 1 in the confining regime, and it's not 1 in the Higgs regime of QCD at high densities. It's e to the 2 pi I over 3 when the quarks are degenerate in terms of mass. And well, so that means that this Aharonov-Bohm phase must change in some non-analytic way with density. So if you increase the density for a while, it stays 1. And then coming in, if you're decreasing the density, if you're coming in from high densities, then it's e to the 2 pi I over 3. And well, it's locked to both of those. So somewhere in between, it has to go from one to the other, and that cannot be done analytically. So it has to evolve non-analytically with density. Maybe as a complete jump, maybe something more complicated, but it has to be non-analytic. So that's already an indication that there's something very interesting happening. There should be a phase transition, I think. But we should be very careful, because the thing that we just defined is not local. The Aharonov-Bohm phase is extracted from a non-local computation, as with any Wilson loop. Therefore, it is completely reasonable to challenge me on this and to ask, how do I know that this non-local thing that we just came up with actually tells us about non-analyticities in practically interesting things like ground state energies? How do we know? And well, we got to answer that question. What we did is we took a detour to 2 + 1 dimensions rather than 3 + 1, which is where the physics is originally most interesting. See, the idea is the following. It is extremely difficult to explicitly check how the non-analyticities in the Aharonov-Bohm phase conspire and not conspire with non-analyticities and ground state energies in 4D non-abelian gauge theories. And the reason is that the transition between the two regimes necessarily occurs with strong coupling. And so we have no idea how to do any calculation there. But the good news is we're asking a kind of question of principle. Do non-analyticities in Aharonov-Bohm phases of vortices imply, are they correlated with an actual thermodynamic phase transition? So that's a question of principle. So if we can find some simpler QFT where the same question can be asked and also answered, that would be really useful. And that's what we did. So we took a detour to 2 + 1 dimensions, where it turns out that we can leverage the fact that confinement is much better understood, at least in something called compact abelian gauge theories in 2 + 1 space-time dimensions. And that's due to the work of Polyakov in the 70s. The technical statement is that electric charge confinement is driven by the proliferation of magnetic monopole instantons, and it can be described using 3D abelian duality. If you don't know what that is, don't worry about it, but there's technical tools that you can use to understand confinement on a piece of paper from the 70s in this case. And we can take advantage of that, and we did. So we found a 2 + 1D abelian gauge theory as a toy model where you can ask this question of principle with Higgs and confining superfluid regimes. And we showed that in that model, first, the superfluid vortex Aharonov-Bohm phases change non-analytically as you go from the Higgs to the confining regime. I'm not going to explain the details of the model just because it's a colloquium and there's not enough time. And those of you who aren't working specifically on this kind of stuff yourself, probably won't care. But what we can show in this model is not just this statement here, but because the model is simpler and confinement is, and many other things are under better control, we can actually show that, well, we can check the correlation between a jump in the Aharonov-Bohm phases and compare that to whether there is a thermodynamic phase transition. If so, does it happen at the same place where the jump happens? And so here's a plot from one of our recent papers where we are varying some parameter that takes us from the Higgs regime to the confining regime. And there is a first order phase transition from a regime where you have some Higgs theory to some confined theory where there's no obvious Higgsing. Phi c here is the VEV of some charged scalar field. Phi 0 is some neutral scalar field, and there's some gauge group. So here the charge field expectation value is 0, and it's a first order transition. We know where it is. It's under complete analytic control. Recoupling methods are reliable. We know it's there, and we can check what happens with the Aharonov-Bohm phases. And the result is that they jump precisely at the transition. That is good news, because it shows that a jump on Aharonov-Bohm phases is in fact associated with phase transitions, where you can check. And well, there are other cases in which you can't do the check on paper, but that's life, right? Physics is hard. There's also a more general heuristic argument, not a proof, but a heuristic argument for why jumps in Aharonov-Bohm phases should be associated with phase transitions. You know, the superfluid ground state contains some density of vortex loops just due to quantum fluctuations. So if the Aharonov-Bohm phases of large vortex loops jumps, then that's associated with some kind of jump in the color magnetic fields carried by the vortices. That's in quotes because it's not really gauge invariant, but whatever that is, it contributes to the energy of vortex loops, at least in any simple semi-classical model you would write. And a jump in the Aharonov-Bohm phases would be giving you a jump in the energy of vortex loops, but the vortex loops are part of the ground state wave function. So if their energies jump, then the ground state energy will jump. And that's a phase transition. And here, every time I say jump, I really mean change non-analytically. Okay. So I'm coming near the end. Okay. So we've considered the Aharonov-Bohm phase of superfluid vortices in dense matter, as well as some other related models and other space-time dimensions, other quantum field theories. But anyway, in cold nuclear matter, this Aharonov-Bohm phase of superfluid vortices is just one due to confinement and string breaking. Okay, so the exponential of the phase is 1, to be precise. The phase itself is 0, not 2 pi. And it's not 1 in cold quark matter, at least in the cold quark matter that you get if you have SO3 flavor symmetry. So where it's actually exactly e to the 2 pi I over 3. That is at least a very strong indication that there has to be a density-driven phase transition between confined nuclear matter and deconfined quark matter in QCD. So we think that's quite strong evidence against quark-hadron continuity in dense matter. So now I should be honest with you. Our calculations to date have all been focused on the 0 temperature limit. We have not carefully studied yet what happens when you take into account finite temperature corrections. It's a very interesting question. There are some subtleties, but at least for the moment, we expect our results to continue to hold at finite temperature. So, so really, we're arguing there must be a phase transition there so far, but ongoing work will be aimed at trying to show that actually there's a curve like that. But again, for the moment, existing evidence suggests that that's actually true. You know, neutron stars are very cold, so showing that there's something happening at low temperatures is already a victory. Although it'd be nice to show it all the way. So let me conclude. So I tried to tell you over the last hour or so about some progress in quantum field theory, and that progress was about trying to understand the distinction between confined phases, confined regimes of gauge theories of fundamental matter and Higgs regimes of the same gauge theories. And it turns out that that question, as I tried to explain, is intimately connected to the question of what is quark matter in QCD. It may sound like different questions, but they're really the same question. And it turns out that that question has an answer. They're really distinct. And the way that you tell is you compare the Aharonov-Bohm phases of superfluid vortices. It's a gauge invariant calculation. It's physical. And the results apply to QCD itself and also to some variety of other theories. I only talked about QCD really. But in QCD, it gives you good evidence for the existence of an extra phase transition, which people had speculated about but did not have an argument for from first principles. There are many issues that are open, that some of which we're thinking about. We're hoping people will think about, other people will think about them. So for example, what exactly is the deal with finite temperature physics? What's the physics in an interface between these two different types of superfluids? That's also interesting. Can we say something about the order of the phase transition? Like right now, we haven't said anything. We just think that there's a phase transition, but it could be first order or second order. Could even be BKT-like, strictly speaking, we don't know. What order the phase transition has will impact the neutron star physics, of course. All of these things can also be asked in various models of interest to condensed matter physics. That's something that we're thinking about now. Maybe there's something to say for the condensed matter community. There might be applications to FPH, namely to BSM physics, but that's more speculative. And the question I really want to know as a quantum field theory person, apart from all of these, is how does this fit into the existing classification of phases of matter in the condensed matter literature, or does it require a generalization of it? I don't know the answer. I have no idea what the answer is, and I'd love to know. I think it'd be really cool to figure this out. So with that, I'm going to stop, and thank you for your attention.
Well, thank you very much for a very, very nice presentation. We do have some questions. So let's start with the first question from Mark Alpha.
Hi, can you hear me okay?
Yes, hi, Mark.
Okay. Hi. Yeah, so the question I wanted to ask was, you talked a bit about the Wilson loop operator as how you make your quark anti-quark pair, but you didn't say anything about what kind of operator is going to make the vortex for you.
That's right.
Presumably you have to have an operator to make the vortex too, and vortices are kind of energetically expensive, so I just wondered if you could say something about that.
Good. So I could give a couple of different answers. So, okay, so the physical answer is, if you want to make a vortex in practice, you take your superfluid and you spin it. Then you make vortices. If the rotation of your bucket exceeds some critical velocity, then you definitely just make a vortex, and now you're entitled to ask what happens when you go around it. Now, you don't have to do it that way. So at least mathematically, you can think of a vortex operator as a kind of defect operator. So you prescribe the circulation of the superfluid order parameter around some curve in spacetime, and that forces the theory to produce a vortex there. That's another way of thinking about it. If you want to think about it that way, then you can describe also like vortex loops very easily. I'm happy to tell you in more detail if you like what I mean precisely by that, but it's very similar to the way you would describe like a 't Hooft loops or anything else. It's just a defect operator. But indeed, they're expensive, but they're there. Vortex and so to say it another way, vortex anti-vortex pairs are there, and in space-time that's like a loop. So that's a finite energy state, and you can ask about it.
Okay, next question from Giorgio Torrieri.
Hi, this is a bit of a, I think it's kind of a follow-up to what Mark asked a little bit, that the thing with non-local operators is that they are also defined and interfere with non-local equilibrium, also within, ensembles away. Let me give you sort of an example. Let's go to zero chemical potential, high temperature.
Okay.
And let's assume that viscosity is small enough that an initial condition with color domains thermalizes on a very short time scale with respect to the size of the color domains.
Okay.
And by the way, if you take results from small systems at the LHC, this is a very likely assumption, because it seems that proton-proton collisions act as ideal fluids with a comparatively small number of particles. So if we assume this, you might have Kähler vortices, you might have hydrodynamic vortices. This is not an equilibrium, it's not a superfluid, it's a non-equilibrium situation, but you will have vortices inside a Kähler domain. And this is exactly your order parameter. This will give you the equivalent of your order parameter, but it's not really an order parameter because you're not in global equilibrium. Maybe you're in local equilibrium in some way.
Yes, that's fine.
Can one learn, can one sort of use your reasoning about the existence of an order, of a, in this case, non-equilibrium order parameter to connect the high temperature phase to the low temperature phase? Because you will also have a non-equilibrium order parameter if you want. Does it mean that you will have some kind of turbulence to non-turbulence phase transition at high temperature?
Well, I should start by being honest that I haven't thought about the non-equilibrium case. Definitely everything that I've said was meant to focus on equilibrium, near equilibrium physics. So I'm really not so sure. I think, there's not so, all evidence says that there's really no phase transition as a function of temperature in QCD, at least if you're in the thermodynamic limit and, in equilibrium at any given temperature. Whether there is interesting non-ellipticities in turbulence behavior or something, I don't know. One thing I want to emphasize is that for our purposes, it was super important that when we ask about this Wilson loop that goes around vortices, that we ask about sort of a very large Wilson loop. So large compared to the microscopic scales in the problem. That's because if you are looking on, if your loop is very small, then you're not resolving any long distance physics. You're probing some short distance stuff, and that short distance stuff tends to be non-universal. So it's important for us to look at long distance properties. And I remember you mentioned Kähler domains and so on, which naively sound like they'd be pretty small. So I would worry about that, but at the same time, I think it's an interesting thing to think about. And I haven't thought about it. Yeah, sorry for that long answer.
Okay, next question is from Misha Stefanov.
Hi, Misha.
Hi. Actually, I wanted to ask another question, but follow up on what you just said. I wanted to ask you this in context. So what do you expect to happen to this Wilson loop or to the phase if you contract the loop?
Yeah, so it will.
What will happen to the phase when the loop becomes microscopically small?
It will start approaching, the phase will start approaching zero and start becoming trivial. So it's the same answer as you would get if you asked your question for a vortex and a superconductor, a standard superconductor. Like if you have a superconducting vortex they carry magnetic flux pi, right? So what we mean by that is that if you compute a Wilson loop that goes around the superconducting vortex at large distances from the vortex core, you get a phase of pi, or e to the I pi, depending on what you're thinking about. And that's only true if your loop is large. If your loop is small, then at some point you're not really describing the flux carried by the whole vortex, but you're describing the flux carried by some random tiny chunk of the vortex. And that's completely non-universal. So, same for us.
You are not saying that the phase could continuously change. I mean, could you have a vortex with or loop with a phase 0.9?
If you vary, sorry. So the thing that the thing that cannot change continuously, or at least analytically, is the phase evaluated on large contours. That's the thing that's quantized in a superconductor. The phase that you compute on a disk that is of varying sizes can be anything you want. It's not quantized. That's true in a superconductor, and it's true for us too. So if you vary the size, that generically the answer is non-universal, but as the size goes to infinity, it becomes universal.
So you are saying that there are finite size corrections to the value of the phase.
Precisely.
Not just to the magnitude of the
Precisely.
pre-exponent, but the phase itself.
The phase itself, and this is no different for us than from standard superconductor discussions. Yeah.
And then the question I wanted to ask is, in your last discussion of finite temperature, do you imply that this phase transition, which you predict, if it's a first order, could actually end, for example, in a critical point? Is it allowed to?
We have not excluded that possibility yet. So here's the challenge, okay? So that we need to think about carefully, and we haven't gotten our thoughts straight about it. So suppose that the quantization of this vortex flux is really a zero temperature statement for some reason, just for the sake of argument. Then you would not have any argument that says that there must be a transition all the way through. And then you would say, well, if this phase transition was first order in the first place, and why not? Generically, things are first order unless there's a good reason. Then it would end somewhere in a critical point, perhaps. But it's not like at the moment, okay, we haven't found any reason to think that these Aharonov-Bohm phases would cease to be quantized at finite temperature. But we're trying to be careful about it. So I don't want to claim that I understand that. There are some analogous questions that can be asked in the topological order literature where the results are a little bit complicated. So we're trying to digest them and trying to see how to apply them here. But yeah, so if it turns out that something funny happens to this quantization at finite temperature generically, then I might expect some interesting critical point. But I'm not sure, because it might all be fine for arguments, and then there would be no reason to expect such a thing.
Thank you.
Yeah.
Okay, the next question is from Geraint Evans.
Yes. Hello, can you hear me?
Yes.
Yes, I can. Hi.
Great. So first of all, thank you for the great talk. It's very interesting.
Thank you very much.
My question is, this might be a bit naive of a question, but so presumably when you get closer to this phase boundary, the individual quark masses become more distinct. Do you see that affecting your argument in any way, or the Wilson loop calculation?
Yeah, good. So so making the quark masses distinct indeed affects the calculation. Let me tell you how. So I think I deleted a certain backup slide that would have been helpful here, but that's okay. I can tell you anyway. So when you break the flavor symmetry explicitly, the Aharonov-Bohm phase, the long distance Aharonov-Bohm phase, is no longer quantized to be e to the 2 pi I over 3. So what it is depends on the quark masses in some somewhat complicated way. However, this result on the confining side, that the phase is trivial, it doesn't use anything about the the details of the quark masses. It's just a consequence of standard ideas about confinement and string breaking. So then coming in from low densities, the Aharonov-Bohm phase is 1, and coming in from high densities, the other thing that we know is that it isn't 1, but it can be something else. But a function which is 1 coming in like this and not 1 coming in like that cannot be analytic. Somewhere it either has to have a discontinuity or at least a non-analyticity. So we predict that there's still a phase transition. But there are further issues, okay, that I have not yet discussed, which is that if you make the quark masses very, very different from each other, like if the strange quark mass is parametrically large compared to the up and down quark masses, then there's an intermediate regime between what I've called nuclear matter and what I've called quark matter. And that is something, so my quark matter regime is this color flavor locked thing. But if you have this large hierarchy between the strange quark mass and the up and down quark masses, there's an intermediate regime, at least one, maybe there are others, called the 2SC regime. where the quark pairing is different, and the global symmetry realization patterns are different from both nuclear matter and from super high density quark matter. And then once you say that, it's obvious there's a phase transition along the way. So maybe I should say the following. The high stakes question is precisely what happens near the flavor C3 limit, because if you go very far from it, then there must be a phase transition between low densities and high densities anyway. In fact, probably more than one. But the question is, what if you're close to the SU3 limit? Then it's much more difficult. And that's where the results of this talk come in and show that in that limit, there also should be a phase transition. That's what's new. Very far from that limit, there definitely are phase transition. And people already knew that, but from standard Ginsburg-Landau reasons. So
Okay.
hopefully
sorry, can I add a question on?
Go ahead.
Of course.
So is there space for quark-ionic matter in that kind of transition region?
Maybe. Okay, so let me just be clear. So everything that I've said is for 3 colors and 3 flavors. Quark-ionic matter is a large N thing, strictly speaking. So you may speculate about what it does as N becomes small, but then you're speculating. And so perhaps those speculations can be made, and there's something that you might want to call quark-ionic. But strictly speaking, if you want to make it precise, you have to go to large N, because that's where the quark-ionic idea originates. And in this talk, unlike in much of my life, which is usually at large N, I've really stuck to small n. N is 3. And then strictly speaking, quark-ionic matter is a very fuzzy notion. So that's why I said I'm not sure, maybe.
Okay, thank you very much.
Okay, the next question is from Kostya Tkachenko.
Yes, hi. Sorry, can you hear me?
Yes.
Yes, I can.
Thanks very much for your talk. My question is, if we don't have rotations and we don't have vortices, would there still be a would there still be a transition between quark and nuclear matter?
I would argue that the answer is yes. So maybe there are 2 arguments. Let me give you the heuristic one first, and then come back and give you a less heuristic one. So the heuristic argument is that when you don't have rotation, it's nevertheless still the case that the ground state wave function contains some vortex loop components, right? So you can, a vortex loop is a perfectly fine excitation of the system, even when it's not rotating. And so a change in the behavior of vortex loops, which is what this is also, at least heuristically, a reason to expect a phase transition. So I think the answer is yes. You would expect all of this to be relevant even if things are not rotating. And a little bit of support for that comes from, like explicit support, comes from our studies in 2+1D gauge theories, where you can be much more explicit about everything. And then you can see that for the parameter choices where you have a phase transition, like a genuine bulk phase transition without anything rotating, if for those same parameter choices, you stick in a vortex, and then you ask about the Aharonov-Bohm phases, the parameter values at which the Aharonov-Bohm phase jumps is exactly the parameter values at which the phase transition occurs. So that sort of lends support to the connection.
Okay. All right. Thank you.
Yeah.
Okay, I don't see any other questions from the audience, but I do have one question of my own. What you basically kind of proved is that there is a certain quark matter phase which is different from a nuclear matter phase, and there is no continuity between these 2 phases. However, it doesn't say that there is a distinction between quark matter and nuclear matter if the first transition first happens from this quark matter to, let's say, some other quark matter like to a C quark matter, and then there is a continuity between that quark matter and the nuclear matter. In that case, you will not be able to say unambiguously that there is a true distinction between quark and nuclear matter. Isn't that right?
I would not,
so
if I understood
correctly, there is a phase
not
transition indeed between low density and high density, but it will go through the continuous transition between nuclear and some other quark matter, let's say to a C. So it's a continuity. And then there is a transition between 2 different quark matter phases.
I don't think that Okay, so basically, okay, what I've assumed is the simplest scenario where there would be one transition. That's what I've sort of been implicitly assuming. It is totally logically possible, and in fact, we have examples in these 2+1D models, which there can be more than one transition. There can be more than one phase transition. That's logically possible. So there could be intermediate phases in between, but then those intermediate phases would be distinct from both nuclear matter and high-density quark matter. So
wait a second.
it's
That phase is not necessarily different from the nuclear matter. That's what I'm saying.
Well,
that new quark phase matter in between, not necessarily distinct from nuclear matter.
Okay, well, so you can ask the following question: if this putative extra quark matter phase, like, first of all, if it has global symmetry transformation properties different from both of the phases I've talked about, then it's separated by a phase transition from them both. So if it has the same global symmetry realization properties, then we have to discuss further. You can ask, is it superfluid? I mean, if it's not, again, we stop the discussion, it's a different phase completely. If it's a superfluid, it's got vortices. Now I can ask my Aharonov-Bohm question. Either the phase, the Aharonov-Bohm phase is one, or it's not one. If it's not one, then it's different from nuclear matter. And by the same arguments that I've given, it cannot be analytic. So it's a distinct phase from nuclear matter. Whether it's a distinct phase from the high density regime, it's already kind of a moot point because it's already different from nuclear matter. We've established at least one phase transition. If the Aharonov-Bohm phase is one, that's the other possibility, then it might well be smoothly connected to nuclear matter, but then it cannot be smoothly connected to high density quark matter. So by arguments like this, I think, yeah, there has to be, what I'm arguing is there has to be at least one phase transition, but there could well be more. It's certainly possible there are more. In fact,
I totally agree with that point of view. It's not a question about that. It's about the sort of, if you wish, philosophical question. Is there a true distinction between quark and nuclear matter? And there may not be for other examples of nuclear and quark matter phases.
Right. I think I see what you're saying.
Yeah.
I think I see what you're saying. So there might be other phases which it is tempting to call nuclear matter and tempting to call quark matter.
Exactly.
And this, whatever this thing I've just defined, may not distinguish them. That is completely logically possible. And then it would raise the question of, well, when one calls them nuclear matter and quark matter, is there any precise meaning to that? Or is it like a matter of convenience? That's back to the old question.
Right. Yeah.
Right.
Exactly.
So very good. I agree. It cannot address that question. Yeah.
Okay, there is actually another question. You could read it in the chat, or I could read it for you from Naoki Yamamoto. He cannot speak. Probably you cannot see it. So what about, say, QCD at finite isospin density instead of finite baryon chemical potential, where a BEC-BCS type crossover between the pion BEC and the weakly coupled BCS pairing of U bar and D is also conjectured? In that case, superfluidity high density matter is not a Higgs phase, as the U and D pairing is called a singlet, yet the effective degrees of freedom, there are quarks. Isn't it possible that quark matter is continuously connected to hadron matter in principle? I suppose it's somewhat along the lines that I was saying. At least theoretically, one can ask a similar question in two-color QCD at finite baryon density, where a similar BEC-BCS type crossover of color singlet diquarks is conjectured.
Good. Very interesting. There's a lot there. Here's what I would say. So first, just to be honest, we have not carefully thought about what happens if we take our discussion and we perturb it with chemical potentials for flavor, for example, isospin. That's interesting, but it would break flavor, and for some of our story, it was useful to sort of maintain exact flavor symmetry, although not necessary, but we just haven't thought about that. But let me comment on two-color, two-flavor QCD. Indeed, in that example, the high-density regime is not a Higgs regime because the condensate is a color singlet. And I mean, I haven't thought about it very much, But certainly because of that, I would expect that the considerations in my talk will not apply. So whether you can distinguish the high density version there from the low density version in some precise, sharp way, I don't know. But I would be surprised if the order parameter that we talked about would help to do that. I suspect that it would not. Nevertheless, it is worth thinking about carefully, because anytime you have some new order parameter floating around in the literature, it's worth, for your favorite model, testing it out and seeing whether it's useful. But we haven't tried that. So I think it's an interesting question. I'd be surprised if it helps, but it might. So it's worth thinking about, but I'm not sure.
Right. Okay. Are there any other questions from the audience? I don't see anybody. Okay, I'll give you another 20 seconds to think if anybody has a question. But using the opportunity, I would like to thank Aleksey for this very nice presentation, patience answering all the questions. So thank you.
Thank you very much, Igor. This has been great. And thank you to the audience. Very fun. Thank you for the questions.
Thank you, everyone, for participation. Once again, if you have any nominations, volunteering for other colloquia, please let me know by email. Otherwise, we are done for today. And thanks, everybody. Most importantly, thanks to the speaker.
Thank you. Bye-bye.
Okay.